Alright, let's take a look at a nice little differential equation problem. And let's just, for the sake of argument, say that cats were accidentally introduced onto an island, right? There's nothing there to be predators on the cats, and that the population would grow at a rate proportional to the current population, and let's call that P. And let's let T be time in years. Now, the first thing we might like to do is write a differential equation that represents the rate of change in the population. Right? P is population, T is time, rate of change per time. Now, we said that that was directly proportional to the population, P. So what we would need is a proportionality constant, K, in the population. Okay. So there is our very nice differential equation. Now, what we might like to do is find a particular solution. And for finding a particular solution, we need some boundary conditions, some initial conditions. So let's say that when we introduced cats to the island, we introduced 6 of them, 6 cats. And that after 2 years, let's not go 2 years, let's go 4 years. After 4 years, there were 87 cats. Right, so P is 87. So now what we can do is use this information to find the particular solution. We start with dp dt equaling kp, and we want to solve this differential equation. Now, solving differential equations is the one time where the default should not be take the derivative. It should be separate and integrate. First thing we want to do is separate variables. So I'm going to multiply each side by 1 over p, and then I'm going to multiply each side by dt. So the p's cancel out, the dt's cancel out on this side, and we get 1 over p dp equals k dt. And now it's time to integrate. The antiderivative of 1 over p is the natural log of p. Antiderivative of k dt is kt plus c. Because remember, k is just a constant. It's a number, like 7 or something like that. So now, we don't really want to know what the natural log of p is. We want to know what p is. So to get rid of this natural log, I can exponentiate on each side. And that gives me p equals e to the kt plus c. But I can use the laws of exponents. That becomes e to the kt times e to the c. But e to a constant is just another constant. C e to the kt. Okay. So P is equal to e to the kt all times c. Now we can come back here and grab our initial conditions. We got 0, 6, and 487. 0, 6, and 487. And we've got P is equal to C times e to the kt. Now remember that these are TP points. Okay, so if t equals 0, that means that e to the kt all equals 1, so that tells me that this c equals 6. So P equals 6 e to the kt. Now, what we really want to solve for next is that constant k. Well, we've got this other point, 487. So the population is 87. That equals 6 e to the k times 4. Okay. Now, the next thing we'd like to do is solve for that k. So I can do that first by dividing each side by 6. So I get 87 over 6 equals e to the k times 4. So now if I take the natural log of each side, I get the natural log of 87 over 6 equals k times 4. So then it's time to get your trusty calculator out and solve for k. Natural log 87 divided by 6 is 2.674, and if I divide that by 4, I get k. So that gives me a k value of 0.669. So then my equation, P equals 6 e to the 0.669 t is my equation for the population at a given time t. Now, what I might like to do also is find out, well, how fast is the population changing when the population equals something like 400? Well, if we remember all the way back to the beginning, we had dp dt. And what is that? That's the rate of change in the population. And we said that that was equal to k times the population at that time. Well, k is 0.669, and if the population is 400, again, another time to get out your trusty calculator. And we multiply 0.699 times 400, and we get 279.6, and the units on that would actually be cats per year. So in other words, when the population is 400, it's increasing at a rate of about 280 cats every year. So hopefully this is a large island, or if someone is walking around there up to their nether regions in cats by this point. Now, let's see. Another thing we could maybe do is find out what's the rate of increase in the population after, I don't know, maybe how about, let's go 7 years. Well, remember dp/dt is kp, and we know that k is 0.699. What we don't know is the population at 7 years, but we have an equation for that. So p is going to equal 6 e to the 0.699 times 7, and that's going to be, as we quickly crank this out, $800.118, but we'll just round it at 800. So dp/dt at 7 years is going to be that growth constant, 0.699 times 800. And I get 559. So, hopefully you're a cat lover, because after 7 years you are getting an extra 559 cats per year. Okay. Now, if we wanted, we could ask ourselves, if we want, what's the limit as t approaches infinity of 6 e to the 0.699t. Well, that's going to be an infinite number of cats, because by the mathematical model, there's nothing to inhibit their growth. They're just going to keep growing and growing and growing until you have a mountain of fur and claws and ears and whiskers and tails, and hopefully you like cats, because that's a whole lot of cats. Well, I hope this helps. You guys have a nice weekend. Enjoy. See you on Monday.